Hello, my dear students. How are you all? I am fine. I am Khandekar Fazle Rabbi, lecturer, Department of Chemistry, Milestone College, Uttara. During this pandemic situation, welcome you all to our online chemistry class. My dear students, today we discuss about some important creative question from chemistry first paper chapter 2 qualitative chemistry. My dear students, our question is calculate the number of orbitals and electrons present in the outermost shell of model A. My dear students, according to atomic model A, we can see that the last electron present in fourth shell. So, the calculation of maximum number of electrons and orbitals in the fourth shell given below, and for fourth shell the principal quantum number n equal to 4. When n equal to 4, L equal to subsidiary quantum number L equal to 0, 1, 2 and 3. When L equal to 0, then magnetic quantum number M equal to 0. When L equal to 1, we get minus 1, 0, plus 1. When L equal to 2, then M equal to minus 2, minus 1, 0, plus 1 and plus 2. And when L equal to 3, then we get the value of M equal to minus 3, minus 2, minus 1, 0, plus 1, plus 2 and plus 3. So, we get spin quantum number 1 into plus minus half for M equal to 0. For L equal to 1, we get 3 value of M. So, spin quantum number equal to 3 into plus minus half. When L equal to 2, then we get 5 value of M. So, here 5 into plus minus half, and when L equal to 3, we get the value of M equal to 7. So, spin quantum number 7 plus minus half. So, according to our discussion, we can say that for L equal to 0, number of orbital equal to 1. When L equal to 1, then number of orbitals equal to 3, and for L equal to 2, number of orbitals equal to 5, and for L equal to 3, number of orbitals 7. And we know that every orbital contains only 2 electrons. So, number of electrons present here 2, 6, 10 and 14. Now, we can say that the total number of orbitals is 16 and number of electrons is 32. So, we can say that the total number of orbitals in fourth shell equal to 16 and the total number of electrons in fourth shell equal to 32. My dear students, our next question is determine The wavelength, color, and energy of radiated light for the transfer of the electron shown in the model A. My dear students, according to model A, the electron shifts from fourth energy level to second energy level. So, according to according to model A, we can say that N1 equal to 2 and N2 equal to 4. So, my dear students, we know that wavelength 1 by lambda equal to RH 1 by N1 square minus 1 by N2 square, and 1 by lambda equal to the value of RH equal to 109,678 centimeter inverse 1. So 109,678 1 by 2 square minus 1 by 4 square, and 1 by lambda equal to 20564.625, and lambda equal to 1 by 20564.625, and we get the value is lambda 4.8627 into 10 to the power minus 5 centimeter. So, the wavelength of the transition, for the transition is 4.8627 into 10 to the power minus 5 centimeter. And if we convert this value into nanometer unit, then we have to multiply here 10 to the power 7. So, lambda equal to 4.8627 into 10 to the power minus 5 into 10 to the power 7 equal to 486.27 nanometer. My dear students, we see that, or we know that the wavelength from 450 to 500 nanometer, from visible range light, the color is blue. So, the color for transition is blue. Here, the wavelength here the wavelength 486.27 nanometer. So the color for the transition is blue. So the color for the transition is blue. My dear students, now we calculate the energy for the transition. So according to the stem n1 equal to 2 and n2 equal to 4, we know that energy E equal to h nu and E equal to h c by lambda. My dear students, we know that nu equal to frequency, nu equal to c by lambda. Okay. Now the value of h is Planck's constant, my dear students. H is Planck's constant, and the value of Planck's constant is 6.627 into 10 to the power minus 34 joule second. C equal to 3 into 10 to the power 8 meter per second, and lambda, we get the value of lambda equal to 486.27 nanometer. To convert this unit nanometer to meter, we have to multiply 10 to the power minus 9. That means 486.27 into 10 to the power minus 9 meter. Okay, my dear students. Now E equal to 6.627 into 10 to the power minus 34 into 3 into 10 to the power 8 divided by 486.27 into 10 to the power minus 9, and we get the value E equal to 4.09 into 10 to the power minus 19 joule. So we can say that for the transition, energy is 4.09 into 10 to the power minus 19 joule. Dear students, our next question is comparison between model A and model B. So according to our STEM, model A is Bohr's atomic model and model B is Rutherford's atomic model. So now we discuss about comparison between Rutherford's atomic model and Bohr's atomic model. My dear students, Rutherford's atomic model is based on general mechanics, but Bohr's atomic model is based on Planck's quantum theory. According to Rutherford's atomic model, electrons can move in any circular orbit of any radius around the nucleus. According to Bohr's model, electrons can only move in certain stationary orbits instead of moving in any circular orbit of any radius. According to electromagnetic theory, revolving electrons around the nucleus will continuously lose energy. Hence, the electron must gradually spiral in towards the nucleus. The radius of the electron orbit will gradually decrease and it will fall into the nucleus. So, the stability of atom cannot be explained by Rutherford's model. But according to Bohr's model, during moving in orbits of definite energy, the electrons do not emit any energy. So, the electrons do not fall to the nucleus by losing energy. Therefore, this model can explain the stability of atom. According to Rutherford's model, continuous atomic spectra should be obtained because of electrons' continuous emission of energy. But in reality, spectral lines are obtained from atoms. Rutherford's model cannot explain the origin of atomic spectra line. According to the postulates of Bohr's model, radiant energy is emitted when electrons jump from higher energy to lower energy. The energy difference between two energy states is fixed. As a result, the frequency of emitted energy is also constant and results in producing line spectra. Bohr's atomic model can explain the origin of atomic spectra. Radius of orbit, momentum of electron, energy and frequency of line spectra cannot be determined by Rutherford's model. Radius of orbit, electrons' momentum, energy and frequency of line spectra can be determined with the help of Bohr's atomic model. My dear students, our next STEM here given element A, electronic configuration n-1 d5 ns1, B3 plus, this is cation, electronic configuration n-1 d5, B2 plus n-1 d6 and C2 plus here n-1 d9. My dear students, here given the value of n equal to 4. So, we can say that n equal to 4. So, n minus 1 equal to 3. My dear students, so we can write here A, electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d, this is 3d5 and 4s1. So, we can see that the electronic configuration of A, the element A is chromium. So, we can say that element A represent the element chromium, and our next electronic configuration for B3 plus, that is B3 plus equal to 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. Here B3 plus, that means 3 electron is released from B element. So, according to this electronic configuration, we can say that B3 plus represent B3 plus represent Fe3 plus, and for B2 plus electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6. So, according to this electronic configuration, we can say that B2 plus represents Fe2 plus, and last electronic configuration is C2 plus. Last electronic configuration of C2 plus, here given C2 plus is 1s2, 2s2, 2p6, 3s2, 3p6 and 3d9. So according to this electronic configuration of C2 plus, we can say that C2 plus represents copper 2 plus. My dear students, according to our discussion, now we solve some questions. Our first question is, according to the stamp, identify the cations with reaction. My dear students, we can see that according to our stamp, Be2 plus is iron 2 plus, Be3 plus is iron 3 plus and C2 plus is copper 2 plus. So first identification is Fe2 plus ion identification. My dear students, if we add small amount of potassium ferrocyanide solution in Fe2 plus solution, then a pale blue precipitation is formed, and then we can say that Fe2 plus is present, that means iron 2 plus is present in that solution. If we add small amount of potassium ferrocyanide solution in ferric ion solution, then deep blue precipitation is produced, formed. And if we see that deep blue precipitation is formed, then we can say that that ion is Fe3 plus, that means ferric ion. Now identification of copper 2 plus ion. If we add ammonium hydroxide solution in copper 2 plus ion solution, first of all pale blue precipitation of alkaline copper salt is formed, which is dissolved in excess ammonium hydroxide solution to form deep blue solution of tetramine cupric salt. My dear students, our next question is, explain Pauli's exclusion principle by determining the 4 quantum numbers of the last 6 electrons of element A. My dear students, what is Pauli's exclusion principle? Pauli's exclusion principle is no two electrons in an atom can have same values for all the 4 quantum numbers. According to our discussion, we can say that the element A is chromium, and electronic configuration of chromium is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5 and 4s1. And according to Hund's rule, the electronic configuration of chromium is like this. And according to our question, we have to calculate the 4 quantum numbers of last 6 electrons present in chromium. So if we write, or if we see the electronic configuration, we can say that last 6 electron present in 3d5 and 4s1 orbital. So if we number this electron, this is E1, this is E2, this is E3, E4, E5 and E6. Now we can calculate the 4 quantum numbers for E1. This electron present in 3d orbital, so n equal to 3 and L equal to 2. When L equal to 2, for this electron we can write here, this is the value of m, -2, -1, 0, +1, +2. So the value of m for E1 equal to -2 and the value of S equal to +12, because this is the first electron for this orbital. And for E2, this one is E2, this one is also present in 3d orbital, so n equal to 3, L equal to 2. For this electron, m equal to -1 and S equal to +12, because this one is also the first electron for this orbital. For E3, this one is E3, n equal to 3, L equal to 2, m equal to 0, S equal to +12. For E4, n equal to 3, because this electron is also present in 3d orbital, the value of L equal to 2, because here the orbital is d orbital, and we know that if L equal to 2, then we get d orbital, and the value of m for this electron, this is +1 and S equal to +12. And for E5, n equal to 3, this is 5th electron, L equal to 2, m equal to +2 and S equal to +12. And the last electron, 6th electron, for E6, n equal to 4, because this electron present in 4s orbital, L equal to 0, because for s orbital L equal to 0, m equal to 0, because when L equal to 0, then m equal to 0 and S equal to +12. So my dear students, if we see the value of 4 quantum numbers for these 6 electrons, we can say that no 2 electrons in an atom can have same values for all the 4 quantum numbers.